Hello, everyone. Today we are going to talk about spring force. Spring force is the force that is from the stretching or the compressing of a spring. Let's dive on in. So this is based off of Hooke's law. Hooke, basically he said there's a proportional relationship between as the force goes up, or as the stretch of the spring goes up, the force that it takes to stretch that spring goes up. It's harder to stretch it. This is dependent on the spring constant. So Fs is our spring force. It's measured in newtons. K is our spring constant. It's measured in newtons per meter. And then X is our stretch length, or the change in length of the spring. It's measured in meters. If you're looking for it on your equation sheet, it is right down here. As I said in the last video, the forces equations are kind of all over the place. So I'm going to definitely point out where they're at when you're looking for them. Let's jump in and look at some problems. So here we've got data from our lab. Let's say we did a red spring and a blue spring. These are different springs than the actual lab that you guys did. And we're going to use this to determine our spring constant for each one. So looking at this, we know, I'm going to start with a linear equation again. We've got y equals mx plus b. Now here we do have a b value. I'm just going to ignore that for this case because it represents just the initial force you need to stretch it at all. But we're not worried about that right now to determine our spring constant. On our y-axis, we've got spring force. And then we've got, so that's our y-axis, looking at that. Our slope, we don't know, so I'm going to leave that in my equation. And then on our x-axis, we have stretch, which we determine stretch as x. So I'm going to leave that there. So that's kind of convenient. The x is the same. So here we've got our slope is equal to something. And if we think back to that Hooke's law equation we just had, our slope is going to be equal to our spring constant. So for our red spring, since we don't have to do any math for this, our red spring, our spring constant would be 25.256 newtons per kilogram. And we get that, newtons per meter. We get that because our y-axis is newtons and our x-axis is not kilometer. Oh, goodness. Goodness, there we go, per meter. And then our blue spring is 44.753 newtons per meter. So the slope of this graph just represents our spring constant. All right, one more example here. A spring below has a spring constant of 10 newtons per meter. If the block is pulled 0.3 meters horizontally to the right and held motionless, what force does the spring exert? So just keeping in mind, if I want to draw a force diagram for this, I've got force gravity downward. I've got normal force upwards. And if there's an applied force to the right, we know there's going to be a force this way because something is pulling it to the right. And we're going to have a spring force this way. Now, these are at rest. So we know that our applied force is going to be equal to our spring force. So we can just use Hooke's law. So Fs equals K delta X. We're looking for the spring force. Our spring constant's 10. Times 0.3, this gives us a force of 3 newtons. I know this is pretty straightforward and easy, but honestly, that's just how Hooke's law is. It's really not that complicated. We will apply Hooke's law when we get to our work and energy unit, but for now, just know that this is a way that we can calculate information about springs.